All right, so what I was saying is that the mass of an atom is mostly in the nucleus, almost entirely, because protons and neutrons are in the nucleus. Electrons orbit around the nucleus, and they make up most of the volume of an atom, but they weigh almost nothing. Okay, so compared to our atomic mass for neutrons and protons, which is around 1, if we go from scientific notation here, you'll see that it's 0.0005486, right? That very small fraction is all that the electron contributes. So when we think about mass of an atom, we actually just consider the protons and neutrons because electrons weigh so little that it barely affects anything. But again, they do occupy most of the space. They're the most of the volume. And that's why Rutherford's experiment concluded that atoms are mostly empty. Electrons are there, but they're pretty small and they don't weigh very much. So, you know, even though they're there, you're not likely to run into them when you shoot a beam of particles there. Okay. Also, they move around quickly, so there's that too. Another fact is that protons are charged. We often say that they're +1 and that electrons are -1. Okay, they actually have a value. This is in Coulomb. That's the standard unit of charge. But it's such a small number that we just decided to change it to -1 and +1, just to keep it simple. Okay. Now, when you think about an atom, if the nucleus of an atom with all the protons and neutrons is 1 centimeter wide, which is, this is actually blown up a little bit, but in your textbook it's 1 centimeter, then the rest of the space occupied by the atom, that's where the electrons are, is very large. It's 100 meters. That's the size of a football field. So if you take a marble and put it in the middle of a football field, the rest of the atom would occupy the whole field. So that's what we mean when we say atoms are mostly empty space. And the nucleus is really, really dense. The protons and neutrons, where all the mass is, are concentrated and really like very, very close together. Okay. So the mass of an atom is from the nucleus, and really the mass of an atom actually comes from protons and neutrons, because that's what's in the nucleus. Okay. It's tiny compared to the rest of the atom. So 1 centimeter marble in the middle of a football field, that's the size that we're thinking of. The rest of the space is made of nothing, which is weird. It feels uncomfortable, but that's actually what it is. Okay. Now, the next advancement comes from a guy named Bohr, Niels Bohr. So Rutherford's gold foil experiment was in 1911, and he figured out that it was mostly empty space, but they have a small, dense, very positive core, which we named the nucleus. And that the electrons that J.J. Thomson found before him must be outside of that. So this picture here is showing us the nucleus, which is positively charged, contains protons and neutrons, and the electrons orbit in kind of random places around that. Okay. Bohr's idea was that instead of random places, the electrons actually exist in certain very specific places. Kind of like if this nucleus is the sun, our planet orbits in a particular place. It doesn't exist in between orbitals. Electrons work like that too. We call these circles here orbitals, and so electrons are moving around all the time, and it turns out that they can jump from one orbital to another. If they go down in orbitals, so closer to the nucleus, that means they're going down in energy. If they go up, that means they're going up in energy. But they can only go up in really predictable ways. So what's weird about the way that electrons behave is they disappear from one orbital and they appear in another one, and they never exist in between. We call that quantized energy. It means that the electrons can only exist in certain places. You can think of it kind of like a staircase, right? Like this first model of the atom is like a ramp. Electrons can be anywhere they want to be on the ramp. In Bohr's model, it's more like steps. So you can't have an electron exist in the middle between steps. They can only exist here or here or here. Okay, so quantized means specific energy levels that electrons can have. Okay, and it turns out that that's more correct than Rutherford's model, where the electrons are just random; they could be anywhere. Okay, so this leads us to some questions, and to answer those questions, we need to know more about the forces of nature. Okay, so there's 4 of them. They're not earth, air, fire, water. Okay, that's a totally different thing. The 4 forces of science are gravitational, electromagnetic, the strong nuclear force, and the weak nuclear force. Gravitational works at really long distances, and you have to have very heavy objects like planets. Okay, so we're not going to talk a lot about gravity in chemistry, because the objects we're thinking about are so small and so light that gravity has almost no effect on them. So electromagnetic forces do affect our particles. They depend on the distance, and it's based on the fact that positive and negative things want to be together. So if I have a positive charge and a negative charge, they're going to hang out. We call that an attraction. And of course, if I have 2 negative charges, they don't want to be next to each other, so they repel. Same thing for 2 positive charges. That's the electromagnetic force. All right. So then that begs the question, if you have a nucleus where all these positive protons are smashed really close together because it's dense, how come they don't just fly away from each other? They should. The electromagnetic force says that if you make 2 positive particles close together, they should fall apart. That's where the strong nuclear force comes in. The strong nuclear force is only active if the particles are very close together, basically if they're touching. Okay, so we have this electrostatic barrier. This is where the electromagnetic forces are dominant. So if we have a proton and another proton coming at each other, we have to get past this initial repulsion. And the only way to do that is if this atom is moving really, really fast. That means high temperature, so the temp is high, and high pressure. Okay, so if we get these moving really, really fast by increasing the pressure and the temperature, we will be able to shoot this particle at this one and overcome the repulsion that 2 positive particles have from the electromagnetic force. And when you get them close enough, if you do this quickly enough, the strong nuclear force takes over. And the way that we think it works is that these ping pong balls get traded between the 2 protons if they're touching. We call these ping pongs mesons. They are a mysterious quantum particle we don't know a lot about, but we do know that they seem to be exchanged between protons and other protons and neutrons in the nucleus. So the strong nuclear force is the exchange of mesons between 2 different things. This makes them stick together because you can't play ping pong if you're 3 rooms away from each other. And this interaction at short distances is stronger than the electromagnetic forces are. And that's why protons stay together. Now, the only place to get the temperature and pressure high enough in nature is in the center of a star. So the way that it works is if you have 2 protons come together, that would be a hydrogen and another hydrogen atom, they will make the next element in the periodic table, which has 2 protons, which is helium. Right now, that's what our sun is doing. Our sun is made out of mostly hydrogen, and it creates energy by colliding 2 hydrogen atoms together and making helium. Eventually, way after we're all gone, this process has to stop because you run out of hydrogen, and your star is made out of helium at that point. If you take 2 heliums and you run them into each other, you get the next thing in the chain, which has 4 protons. So if you look at your periodic table, you can find out what element that is. I want you to fill that in. Okay, and if we take 2 of those where we have 4 protons and another 4 protons, you would get the element that has 8 protons. Or we might even be able to take one of these 4 proton particles and combine it with a helium, and we would get 6, which is carbon. Okay, so this process keeps going on and on. You keep colliding protons together, getting bigger and bigger in the nucleus. until you end up with iron. Iron is element number 26, so that means it has 26 protons. The heaviest thing that you can make in the heart of a star with any, large amount of particle anyway, is iron. Once you get to iron, the star is so massive that it can't hold itself together anymore and it explodes. We call that a supernova. Well, actually we call it many things, but supernova is one of them. When a star explodes, all the elements that it ever had in it get scattered all over the universe. And if you're lucky, enough elements might come together to make a new planet, hopefully with some carbon on it, hopefully with some oxygen, some water, etc. And eventually that planet might become the Earth. So, in effect, all of the elements in the universe have come from a star somewhere that's dead. And all of the elements that make you were stardust. So it's a really eloquent way of thinking about this process. That's what we think happens. And we have a lot of evidence for this, so it's a good theory. So once we've made elements, which are certain types of atoms, right? So atoms are the smallest elementary particle. A particular number of protons makes it whatever element it is. So like, again, carbon has 6 protons, right? That's the element that we call carbon, right? So it's an atom and an element. Elements cannot be decomposed by chemical reaction because they're the simplest thing that can be made, right? And so some examples of elements that I like carbon, I like platinum, I like iron, I like all the elements actually. So we could sit here all day, there's 118 of them. But anything on the periodic table is an element. And the thing that makes them different is the number of protons. So carbon has, carbon has 6. Platinum's all the way toward the bottom of the periodic table. It's in group 2, period 6. Platinum has 78 protons. And we just said that iron is element number 26, so it has 26 protons. So if you take a look at your periodic table, you'll find that the atomic number is the bold one to the bottom left of each symbol. That is the number of protons. So I want you to list, I don't know, say like 3 elements here and tell me how many protons they have. You're going to have to use your periodic table to do that. Now we can take different elements and combine them chemically to make compounds, which are sometimes called molecules as well. Some of the compounds we already know include water, where if we take 2 hydrogen atoms and 1 oxygen atom, it will make the compound water. CO2, carbon dioxide, we also know. Carbon monoxide we talked about, right? So anytime you've got the combination of 2 or more different elements, sugar, well, glucose anyway, is this chemical. 6 carbons, 12 hydrogens, 6 oxygens. That's what glucose is. That's a compound. Okay. Our diatomic elements are not compounds. So hydrogen, for example, is an element because it only has 1 type of atom in it. That makes it a pure element. Okay, so don't get confused by that. The diatomics are elements, not compounds. Okay, so once we found out about protons and neutrons and electrons, we started studying the elements in greater detail, and we learned that it turns out there is more than one kind of each element. There isn't a single element in the periodic table that doesn't have possible isotopes. So an isotope is what happens when the number of protons is the same. So in this notation, we put protons on the bottom left. So hydrogen always has 1 proton. That's our definition for what hydrogen is. And then this number on the top is the mass, right? So the mass is equal to protons plus neutrons. So the most common form of hydrogen is something we call protium, which has just 1 mass unit because it's just 1 proton and 1 electron. And we said the electron's mass doesn't really affect anything, so we don't count it. There's also the next most common isotope is called deuterium. Deut meaning 2, right? And so that has a mass of 2 because it's 1 proton and 1 neutron. Tritium is the least common version of hydrogen, and it's made out of 1 proton and 2 neutrons. And those are all the isotopes that we know of hydrogen. There might be more because, you know, it's always possible. But currently, those are the ones we know about. The thing that's the same is the number of protons. That makes it all hydrogen, so it's all going to react the same way. However, deuterium and tritium are heavier than protium is, and also less common. Okay. So these 3 substances are the same element, but we call them isotopes because they have different masses. One other thing that might be different, other than mass, is that only deuterium and tritium are radioactive. Protium isn't. So most of the hydrogen in the universe is not radioactive, but there is some deuterium and tritium in the world and in the universe, and it is radioactive. So similarly, there are oxygen isotopes. The most common one is oxygen-16. It has 8 protons and 8 neutrons, which would look, you know, have 8 electrons surrounding it as well. Elements have, by the way, all elements have the same number of protons and electrons because they have no charge. So if we have 8 protons, then we've got to draw 8 electrons around it. So that's where those come from. Now, the isotope of oxygen still has 8 protons and 8 electrons, but because its mass is 18, that means it has to have 10 neutrons. So there's a little formula that's kind of hidden here. We said before that protons plus neutrons equal mass. That means that if I know the mass, say it's 18, I can subtract the number of protons to figure out how many neutrons were there. So this is a very, whoops, I drew through it, but that's a very handy formula to remember. So it's the mass minus protons gives you the neutrons. All right, and for elements, we figure out the number of electrons because it's going to be equal to the number of protons. So these are the relationships we can use. Okay, so here's your formula. You have the atomic mass minus number of protons is equal to the number of neutrons. Now we want to note that atomic mass is just the total protons and neutrons. This has to be a whole number. Okay. So for example, if we look at cobalt, the periodic table has this mass on there. It's in the upper left corner of the periodic table. This is not a whole number. This is an average value of all the isotopes that exist. Now I know that the isotope 59 cobalt is the most common because that's the nearest whole number, right? 58.9 rounds to 59. It still has 27 protons. By the way, I also could probably guess that since this is lower than 59, there's probably an isotope of cobalt that has a mass of 58, okay? Just a guess. It could be 57 as well if it was really rare, but I'm going to guess it's probably 58 based on our mass here. So the mass on the periodic table isn't the same as the mass we're referring to here. It has to be a whole number to use it in the equation to find neutrons, right? So but protons is 27 from the atomic number. The number of electrons is going to be exactly the same because it's an element. And I can get to the number of neutrons by taking the mass. We're going to assume the most common one and subtracting the number of protons. So this particular example of cobalt has 32 neutrons. Okay. Now I want you to do the same thing with carbon 12, iron 56, polonium. Polonium is a hard one to find on the periodic table. It's pretty far down there. Okay. But it's kind of on the bottom right corner near the stairs. But we're going to do polonium with a mass of 210. And then finally cesium. And cesium has the most common isotope is a mass with 133. So use these, and I want you to tell me how many protons, neutrons, and electrons. Let's make a little chart here. Oh, goodness. Protons, neutrons, and electrons are present for each one of these. So you can pause the video and go ahead and do that, and I'll grade it when you turn it in. Okay, so this notation I've been using is summarized here. You put the mass in the upper left corner, the symbol in the middle, and the atomic number down in the lower left. Now, sometimes people don't bother with the atomic number because if you know the symbol, the atomic number is implicit, meaning that if you can look at the periodic table and find the number of protons. So sometimes, like in the last slide, we just write the 12 here. By the way, the answer to the last slide for carbon is right here, right? There are 6 protons because it's atomic number 6. 6 neutrons because the mass is 12 and we subtract the number of protons to get neutrons, and then 6 electrons. So it's quite a balanced particle. I want you to do the same thing here, but this one is carbon 8, okay? You're going to write the isotopic notation. It's going to be an 8 in the top. Oh wait, it says 8 neutrons. That's not what goes in the top, right? Okay. It's going to be the mass, which is 8 neutrons plus the protons. And we already said that carbon has 6 protons, so I'm going to just add 6. So that means I would write a 14 here and a 6 down here. Okay, so do the same thing for oxygen and uranium.